Hi everybody, I am Francesca Bacciotti and I work at INAF, Osservatorio di Arcetri in Florence, Italy. The study that I want to present today is a polarimetric analysis of the disks around two young T-Tauri stars, DG-tau and CW-tau, and I will show that we have found from this study interesting clues on the dust properties. I list in this slide my collaborators in the study and the main projects that have been funding us. The original aim of the analysis was to find validation for the magneto-centrifugal theory of the jet launch. This is relevant for the nature of disks in the planet-forming region, because if jets are accelerated by this mechanism, they can carry away angular momentum, and so the disk is braked magnetically, and this can influence the mechanisms of formation. Observationally, this theory has been already receiving support from the observations of signatures of jet rotation that we have been finding since 2002. But we need an ultimate test. We need to prove that the hourglass that shapes the magnetic surfaces can be really observed. And we need to do it in systems in which we have already tested the rotation of both the disk and the jet. For this reason, we have identified as optimal targets DG-tau and CW-tau, because these are two class 2 sources with jets. We have already found in them signatures of jet rotation, and the jet rotation matches the rotation of the disk in both systems. So they appear to be ideal targets for this kind of study. So we asked time of obtained observations and obtained data in linear polarization in band 7. And these diagrams present you the main results. And for both jets, we show here the polarized intensity. Superposed, we show contours for the total intensity. And the pattern of the polarization vectors is shown as red segments. We also have reported in these diagrams the direction of both red-shifted and blue-shifted lobes of the jets. The study is published in APG Letters in the reference written here, and I will list in the following the main conclusions of our work. First of all, the origin of the polarization. Unfortunately, the original aim was to find a magnetic field, but the polarization pattern that we find is not consistent with a polarization mechanism due to the magnetic field. Indeed, we see that the polarization pattern is parallel more or less with the disk minor axis in both systems. So this is a strong indication that the polarization is produced not by the magnetic alignment of grains, but by self-scattering of the dust thermal radiation. But also in this case, we can find important clues on the nature of the systems. In particular, we can compare our data with simulations of self-scattering in disks. In particular, we have been finding useful the models by Yang et al. Published in 2017. And comparing our data with those simulations, we see that we find a good agreement if we assume that the disk is optically thick and geometrically thin in the case of CW-tau, while in the case of DG-tau, the disk must have a moderate optical thickness, but it has a flare geometry. So it is not geometrically thin, but it has an opening angle. And this is because you see that the DG-tau intensity shows a peak which is not symmetric with respect to the center of the disk, but it is higher in the near side of the disk. That in our case is indicated by the direction of the redshifted jet. And the same we observe in the simulations. So here we find that the scattering properties of the polarization can indicate us something about the geometry of the disk, namely the degree of settling of the grains toward the midplane. Another important indication comes from the measurements of the polarization fraction. The average polarization fraction is very low in both systems as expected, but it is different. It is less than 0.7% for dg-tau and more close to 1.2% for CW-tau. If we compare these values with diagnostic diagrams of theoretical works, especially the ones in Kataoka et al. 2017, we can derive that the maximum grain size in these disks is different for the two sources, and it is higher for the CW-tau source, in which you find a maximum grain size of around 100 microns, while the maximum grain size is less than 70 microns in the dg-tau case. If we combine this data with the flatness of the distribution, we derive that probably the dg-tau disk is less evolved than the CW-tau, which is actually consistent with other studies. But we have also found an important indication in our pattern regarding the connection with possible substructures that are not immediately clear in the continuum emission in the total intensity. In the dg-tau case, we see that there is a change in the orientation pattern, in the orientation of the pattern at distance from the center, and in particular, there is a change of the orientation in correspondence of a ring in which we start to see emission from formaldehyde, H2CO. So this means that the configuration of the polarization pattern can give you indications of substructures which are hidden at the first sight in the disk. In this slide, I show what is our work in this moment. On one side, we are trying to make comparisons with models that are tailored to our sources. And in particular, we are working with the group of Lin et al. In order to simulate what are the properties of the polarization in disks that have the same parameters of our sources. We are also planning other ALMA observations at the highest resolution possible and in other bands for similar Titori disks. This is our summary. Polarimetry in ALMA band 7 of CW-tau and dg-tau disks shows that self-scattering is the mechanism that dominates the polarization at 0.087 millimeters. And from a study of the dust settling, we see that the dg-tau disk is flatter than flared, while the CW-tau disk is more flat, which means that probably the disks is already more evolved in CW-tau disk because there is a higher settling toward the midplane. This is confirmed by an indication that polarimetry can give on the maximum grain size, as the CW-tau disk appears to have larger grains of the dg-tau disk. And finally, we have shown that polarization patterns can be connected with the presence of substructures that are hidden at the first sight. So, in conclusion, polarimetry can be a powerful tool to probe the dust evolution and the hidden substructures in young disks. Thank you.